Hello everyone, my name is Sinan Kalkan from the Department of Computer Engineering, Middle East Technical University. It's my pleasure to deliver the second part of our tutorial. Note that our tutorial has three parts. In the first part, my colleague Emre introduced the basics of evaluating visual detectors. Namely, he motivated and briefly described different visual detection tasks. Then he talked about different localization qualities used in visual detection tasks. After that, he introduced commonly used performance measures in visual detection. Finally, he provided a quick overview of the recently introduced performance measures. In this part, in the second part, now I will talk about the analysis of performance measures for visual detection that we performed in our recent paper. And in the third part, my colleague Kemal will cover how performance measures can be optimized. Let us look at closely what we are going to talk about in this part of our tutorial. We have two main sections for this part of our tutorial. In the first section, we will look at first how we can analyze and compare performance measures. For this end, we will first introduce some important features that we expect a performance measure to have. These features will facilitate analyzing how good a performance measure is for evaluating different visual detection tasks. Then we will evaluate average precision and panoptic quality with respect to those important features. We will see that average precision and panoptic quality do not satisfy some of the important features that we expect from a performance measure. In the second section of this part of our tutorial, we will first introduce localization, recall, precision error in detail. Note that Emre provided a brief introduction to LRP error in the first part of our tutorial. In this part, I will provide a more detailed introduction. And I will show that LRP error actually satisfies the important features expected from a performance measure. Finally, I will provide a comparison of LRP error with average precision and panoptic quality in terms of their theoretical aspects and empirical behaviors. Okay, let's start with the first section of this part of our tutorial. In this section, as I mentioned before, we will introduce three important features and analyze average precision and panoptic quality with respect to those features. Let us look at the important features that are expected from a performance measure. These important features are completeness, interpretability, and practicality. Now let me introduce them in detail. The first important feature is completeness. We would call a performance measure complete if it considers precisely all three performance aspects of a detector. To motivate why we expect a performance measure to be complete, consider the object detection problem. We can easily extend this example to other visual detection problems. In object detection problem, we are provided an input image as shown here, and we are interested in finding the boxes that bound or surround the objects in the image. This detection problem includes two tasks. A classification task for finding the class labels of the objects, zebra in this example image, and a localization task for estimating the coordinates of the box that bound the object. The coordinates of the center and width and height of the box, for example. We can clearly see that the object detection problem includes two tasks, a classification task and a localization task. Therefore, the performance measure designed for evaluating object detection problem should quantify both aspects of the detection problem. This includes false positive rate and false negative rate for the classification aspect of the problem, and the localization error for the localization aspect of the problem. If a measure is not evaluating any of these quantities, then it's not completely quantifying all aspects of the detection problem, as it is missing at least one aspect. And we will call such a measure incomplete. The second important feature is interpretability. We would call a measure interpretable if it provides insights on the strengths and weaknesses of the detector. In other words, detectors can have different characteristics. One can be good at, for example, classification, while another detector can be good at localization. And we expect the measure to provide insight about these different performance characteristics. To illustrate, let us look at the object detection problem again. Here we have an example input image, and let's say we have a detector that detects these 2 objects out of the 4 objects drawn in blue. Here we see that detector 1 is not providing an ideal performance, as it's providing a high false negative rate. We can easily find another detector which provides high number of false positives instead, and we can consider another detector that provides high localization error instead. If a performance measure does not provide an insight about these different performance behaviors, then it's difficult to understand what is wrong with our detector, and we would have difficulty comparing the performances of different detectors. Therefore, a performance measure should provide an interpretability insight about the performance of the detector. The third feature is practicality. We can call a performance measure practical if it provides some practical benefits and if it does not have any practical issues during its calculation. What could those benefits and issues be? For example, are we able to apply the measure if we have the so-called hard detections? In other words, detections that do not have any confidence scores. Or is the measure able to provide any help for finding the optimal confidence threshold for the detections? Is the measure robust to design choices? For example, to the interpolation or approximation of a curve, or the number of detections per image or class. We will see that performance measures have different benefits and issues when they are applied in practice. Now, let us look at the commonly used performance measures and analyze where they stand with respect to those important features. Let us start with average precision. My colleague Emre introduced average precision in the first part, so I will directly start with analyzing average precision with respect to the important features. Let us look at average precision in terms of the completeness feature, our first important feature. Consider these 3 different detectors which have very different classification and localization behaviors. When we look at their precision and recall curves, we see that they are actually quite different, indicating different problems with the detector. However, if you calculate average precision as the area under these curves, we see that actually average precision value is the same for all these 3 detectors. In other words, average precision does not consider all performance aspects, especially localization. Let us continue with the second important feature, interpretability. We expect a measure to provide insight about the problems of the detector in the interpretability feature. Consider the same example from the previous slide, where we have 3 different detectors with different performance characteristics. We see that average precision provides the same performance of 0.5 for these very different performance behaviors. As such, users of these detectors would not have any idea about which parts of their detectors are failing and which parts are performing well. Therefore, we say that average precision does not satisfy the interpretability important feature. Now let us look at some practical issues which might arise when one uses average precision. First of all, average precision is not suitable in settings where the detections do not have confidence scores. Why? Because average precision is a ranking-based measure and it assumes confidence values to be available for ranking the detections as shown here, and for calculating the precision recall values for each detection and plotting them and obtaining the precision recall curve. If confidence scores are not available, one can calculate only a single precision recall value. Another practical issue with average precision is that it does not facilitate finding an optimal threshold for the confidence of detections. If you lower the confidence threshold, average precision increases because we go towards higher recall values and a larger area under the precision recall curve is covered. With a threshold of 0, all detections are included and average precision obtains its maximum value. Therefore, by looking at average precision values, we cannot determine the optimal threshold. Another practical limitation of AP is that it is sensitive to how it is calculated. After the precision recall curve is calculated from the precision recall values of the detections, we see in general these ups and downs, which are generally smoothed by using interpolation. Then, at a discrete set of recall values, precision is calculated and averaged in order to approximate the area under the curve. We have shown that these steps significantly affect the calculated AP values for classes with few examples, and therefore the calculated AP values may not reflect the true performance of the detector. One final note about the practical issues regarding average precision is that it is sensitive to the number of detections allowed per image, which is the standard mechanism for evaluating detectors in detection benchmarks. This is, for example, 100 detections per image for the COCO dataset. It has been shown last year by Dave et al. That this can actually introduce some bias against less frequent classes. This limit can be changed and defined for each class, which however still introduces a bias in AP against certain classes. If we summarize our analysis of average precision with respect to the important features, we see that average precision does not satisfy any of the important features we defined. To be specific, average precision is not complete, it is not interpretable, and it has several practical issues when we use it in practice. Now, let us continue with the analysis of panoptic quality, which was introduced in the first part of our tutorial. Note that panoptic quality was proposed independently with LRP error and in a similar time frame as LRP error. Let us analyze panoptic quality in terms of the completeness feature, like we did for average precision. We see that panoptic quality can be written in this form, which includes the number of false positives, the number of false negatives, and a localization error for each true positive. Therefore, we can say that panoptic quality satisfies the completeness feature expected from a performance measure. If you look at interpretability, we see that panoptic quality is doing better than average precision in this regard as well. One can easily rewrite panoptic quality and show that it has two main components. A component for measuring the segmentation quality and another component for measuring the recognition quality. Segmentation quality is an average of intersection over union of the true positives, and recognition quality is evaluating the classification performance, and it is an F measure. Therefore, since panoptic quality has interpretable components, it satisfies the interpretability important feature. However, the recognition component is an F measure, and it is not able to distinguish between different precision and recall performances. Therefore, we can say that panoptic quality satisfies the interpretability feature, though it has a limitation in this regard. If you look at the practicality aspect of panoptic quality, we observe that the authors in their original paper applied panoptic quality only to panoptic segmentation, and it is designed to evaluate only hard detections. The authors assumed that segments did not have confidence scores. However, in theory, it's possible to apply panoptic quality to soft detections by a simple thresholding operation. A more severe practical issue with panoptic quality is that it over-promotes classification with respect to localization. Here we see an example. Consider that we are slowly increasing the quality of our segmentation by adding these slices, step by step. With each step or slice, we calculate the corresponding panoptic quality and we plot it here as shown at the right hand side. Here we see that when a detection becomes a true positive, there is a jump in the panoptic quality value. And after this point, the contribution of the localization quality is minor, corresponding with respect to the classification performance, and its localization quality can contribute only between 0.5 and 1. Because of this discontinuity, PQ does not satisfy the triangle inequality and it is not a metric. A more detailed proof of this is available in our paper. We will show later that the way panoptic quality combines classification and localization is actually inconsistent. To summarize, we have shown that panoptic quality is complete because it takes into account false positive rate, false negative rate, and localization error for true positives. It is interpretable because it has two components, segmentation quality component and recognition quality component, but limited in terms of interpretability because the recognition component is an F measure and it does not provide information about precision or recall independently. Finally, it has certain practical issues when it is used in practice. Now, let us look at localization recall precision error, in short LRP error. First, I will introduce LRP error in detail. Then we will analyze LRP error in terms of the important features similar to how we analyze average precision and panoptic quality. Note that LRP error was introduced independently from panoptic quality in 2018. In the first part of our tutorial, Emre introduced LRP briefly, and now I will provide a more detailed coverage. LRP error includes the number of false negatives, number of false positives, and a localization error for each true positive normalized with respect to 1 minus localization threshold tau. We can call this part total matching error, which is normalized by the total source of error in order to make sure that LRP takes values between 0 and 1. We can rewrite LRP error as a summation of three components: a localization component, a false positive component, and a false negative component. Let us go through an example to see how LRP error can be calculated. Let's go through this example image for which we have these objects as ground truth. Let's consider a detector which provides these boxes as detections. If we threshold these detections by 0.95, we obtain a single object. And for this case, the number of false negatives is 2, the number of false positives is 0, and we can easily calculate the localization error normalized. We can add them up, obtain total error. We can normalize it with 3 and obtain an LRP value of 0.70. We can lower the threshold and obtain a second object detected. Then the number of false negatives is reduced. We can calculate the number of false positives, the other quantities as well, and we can easily calculate the number of LRP error. We can lower the threshold even further, obtain a third box, third object. We easily see that the LRP value is reducing with the addition of each object. If we lower the threshold too much, we end up with a false positive as the output of the detector, and we see that the number of false negatives is now 1 and the LRP value increases. If you look at all these LRP values, we see that it is lowest for this threshold. So among the LRP values, the lowest LRP is called the optimal LRP value, and in this case it is 0.47. And we can analyze the components of LRP for this optimal setting, and it gives important cues about the performance of a detector. And this threshold that led to the optimal LRP value is critical. We can easily formulate this optimal LRP error as the smallest of LRP values that can be obtained with different thresholds on the confidence score. If we disregard localization on the precision recall curve, this would correspond to an optimal precision recall value, which is this point, the point closest to 1, 1 on this curve. However, in LRP we have three axes: precision, recall, and localization. And optimal LRP is the point on this curve that is closest to 1, 1, 1. In a 1D plot, we can plot confidence score thresholds with respect to LRP values, and optimal LRP is actually this point, the minimum point of this curve. And this score is then the optimal threshold for this detector. Optimal LRP has three components, and looking at these components gives an intuition about the performance of a detector in terms of localization, false positives, and false negatives at its best setting. In LRP, plotting confidence scores against LRP values gives important clues about the detector. We find these plots very important, and we call them S-curves. We can analyze the S-curves for different detectors and for different classes. For example, for the person class, we see that faster RCNN is providing its best values around 0.60 LRP with a confidence score of 0.70, whereas it provides its best performance with a confidence score of 0.50. We see that S-curves can provide insights, similar useful insights for other detectors and for other classes as well. We can draw an important conclusion from these curves. These S-curves suggest that detectors should have different thresholds for different classes. Why? Because the optimal LRP values are obtained for different thresholds, for different classes. Moreover, we see that detectors provide very similar optimal LRP values for the broccoli class, whereas that is not the case for the person class. After having introduced LRP in detail, now let us look at how it fares in terms of the important features we introduced. Let's start with the completeness feature. In terms of completeness, we see that LRP includes number of false negatives, number of false positives, and localization error for true positives. Therefore, we can easily say that LRP is complete. In terms of interpretability, we can rewrite LRP error as a summation of three components: a true localization component, a false positive component, and a false negative component. Therefore, using LRP error, we can interpret the types of errors a detector is making. Therefore, we can say that LRP error is interpretable. If you look at the practicality feature, we showed in our paper that LRP error can be used for hard detections and soft detections. LRP error does not require any interpolation or approximation, and unlike average precision and panoptic quality, LRP error is a metric. Therefore, we can say that LRP error is actually practical. It does not have any practical issues in practice. If we summarize how LRP error performs in terms of the important features, we showed that LRP is complete because it considers false positive rate, false negative rate, and localization error, similar to panoptic quality. It is interpretable because it can be written as a summation of three components: a localization component, a false negative component, and a false positive component. And it does not have any practical issues when we want to use LRP error in practice. Therefore, we can say that LRP error satisfies all three features, unlike average precision or panoptic quality. Now, let's go through some theoretical and empirical analysis to get more insight about these measures. To be able to better compare average precision, panoptic quality, and LRP error, let us transform all of them to be error values. In other words, after this transformation, all of them will be lower better measures. Average precision uses soft predictions. For comparison with LRP and panoptic quality, we use its hard counterpart, which corresponds to a single precision and recall value. We can transform this precision recall into an error by subtracting their multiplication from 1. Let's call this precision recall error. Panoptic quality can be transformed into an error by subtracting it from 1. Let's call this PQ error. We can easily show that PQ error can be written in this form, where we have number of false positives, the number of false negatives, and a normalized localization error for each true positive. The normalization here is 1 minus 0.5, where 0.5 is the localization threshold. And we have a normalization constant here, which is a summation of number of true positives multiplied by 2, number of false positives, and number of false negatives. LRP is already an error, so we don't need to do any transformation on that. And we already saw that it includes number of false positives, the number of false negatives, and a normalized localization error. And the normalization constant here is the number of true positives, the number of false positives, and number of false negatives. We see that PQ error and LRP error are actually very similar to each other, except for two parts. One part is that the normalization constant has a multiplier in front of the number of true positives for PQ error, and this favors the number of true positives more than it does the number of false positives and the number of false negatives. The second difference is with respect to the localization quality. In PQ error, localization quality is normalized with respect to a constant localization threshold, whereas in LRP error, this is a hyperparameter. When we look at how these errors are distributed in a three-dimensional space, spanned by the number of true positives, the number of false positives and false negatives, and localization quality, we see that LRP error is uniformly and continuously changing with a change in n of the axis, whereas average precision or its error version does not include localization. Therefore, a change in localization quality does not affect PR error or average precision. When we look at panoptic quality, we see that panoptic quality is not consistent about how much it is changing with a change along different axes. The reason is this denominator, where we have a constant multiplier in front of the number of true positives, which favors true positives more than false positives and false negatives. Therefore, it's not consistent in terms of how it handles localization quality, true positives, and false positives plus false negatives. If you plot LRP error with respect to 1 minus precision, 1 minus recall, and 1 minus PQ, that means the PQ error, we see that LRP is always higher than these values for different LQ values. Therefore, LRP can be considered as an upper bound for 1 minus precision, 1 minus recall, and 1 minus PQ. And in turn, this means that optimizing LRP is actually a more challenging problem than optimizing the other measures. If you compare all measures in terms of important features, we saw that average precision does not satisfy any of the features. Panoptic quality performs better than average precision in that it is complete. It is interpretable, though its interpretability is limited, and it has some practical limitations. We saw that LRP satisfies the three important features, and therefore we can say that it is a more suitable measure than others for visual detection problems. Now let us look at some experiments that illustrate the use of these measures. We can look at soft detection problems, such as object detection, key point detection, instance segmentation. We can analyze and compare these measures on hard detection problems, such as panoptic segmentation. We can analyze these measures on different datasets and different detection tasks. And we can show that LRP actually can be used for optimally thresholding a detector. But because our time is limited, we won't be able to look at all the empirical results that we have. And if you are interested in more comprehensive results and analysis, you can check out our paper. In our paper, nearly 100 state-of-the-art visual detectors from 7 visual detection tasks using 10 different datasets are used to empirically show that LRP error provides richer and more discriminative information than its counterparts. If you look at the object detection problem, which uses soft detection outputs, in that we have confidence scores for each detection, we see that average precision actually is not capturing the overall performance of a detector very well. For example, NAS FPN is expected to perform better than GHM in terms of localization, and with average precision, to compare the performance of detectors in terms of localization, average precision at 0.75 intersection over union threshold is used, and we see that actually AP75 value for NAS FPN is actually lower than that of GHM, which is counterintuitive. If you look at the optimal LRP values, the localization component of optimal LRP, we see that as expected, NAS FPN is actually doing better than GHM in terms of localization quality. If you look at average precision in terms of interpretability, we see limitations as well. For example, if you compare faster RCNN with ATSS, APC values are the same, whereas AP at 0.50 and 0.75 intersection over union thresholds are different, and average recall values are different as well. As such, average precision, overall average precision is not sufficient for comparing methods, and AP does not provide an insight about the characteristics of the performance. If you look at LRP on the other hand, we can clearly see that ATSS is doing better than faster RCNN in terms of localization, and faster RCNN is doing better than ATSS in terms of false positives and false negatives. Therefore, with this simple analysis, we can see that LRP provides more insight about the weaknesses of a detector and its strengths. If you look at these measures in terms of practicality, we see that LRP can be used for soft or hard detections, for optimally thresholding detectors, and it does not have any interpolation or approximation issues. If you compare panoptic quality and LRP in terms of completeness, we see that both are complete, since they both incorporate the number of false positives, the number of false negatives, and localization while measuring performance. In terms of interpretability, both methods are interpretable. They provide performance in terms of localization and classification. However, PQ uses an F measure in the recognition component, which is not interpretable in terms of precision or recall. Finally, in terms of practicality, panoptic quality has certain limitations. As we noticed before, panoptic quality over promotes true positives, and there's a discontinuity in PQ values. In our paper, we evaluated these measures on different tasks and datasets with different characteristics. For example, on the Elvis dataset, we did an analysis with respect to rare classes. We looked at the effect of increasing the number of detections per image. We realized that every average precision is severely affected by this change, whereas LRP is more robust against this change. And we have more results on open images, Pascal and Coca datasets on different types of categories, object categories. If you look at a different detection task, for example, visual relationship detection or zero-shot detection, we see that LRP is providing more insights than average precision in all these problems. We also analyzed how optimal thresholding scores for different detectors change. We note that different detectors have different optimal thresholding score distributions, and these scores depend on classes. Our results confirm that thresholding detections differently for each class can be beneficial. We note similar behaviors among different class categories, rare, common, and frequent class categories, for example, and similar observations can be made for different zero-shot detection approaches. We can conclude the second part of our tutorial with these results. In this part, we introduced 3 important features with which we can analyze different performance measures for visual detection. With these important features, we saw that the widely used average precision measure has significant limitations in terms of completeness, interpretability, and practicality. Our analysis on panoptic quality indicated that panoptic quality is doing better in terms of these features. However, there are certain practical limitations with panoptic quality as well. We introduced LRP error in this part in detail as an alternative, and we showed that it does better than average precision and panoptic quality in terms of these important features. Now we will give a break, and after the break we will continue with the third part of our tutorial. Thank you.